Hi everyone, and welcome to today's Safety and Health webcast, Weld Fume Control, a review of OSHA's feasible and effective control solutions, sponsored by Miller Electric Manufacturing Company. My name is Kevin Drulli. I'm an associate editor with Safety and Health magazine, and I will be moderating today's session. Thanks for joining us. In a few minutes, we'll start the presentation, but first I want to go over some preliminary items. The views of today's speakers and organizations are their own and do not necessarily reflect those of the National Safety Council or Safety and Health magazine. Any mention of a commercial enterprise, product, or publication does not mean the council or magazine endorses those items. At the end of today's webcast, we will conduct a question and answer session. To ask a question, simply type it in the text box in the lower left-hand corner of your screen and click the button for Submit Question. Feel free to ask your question at any time during the presentation. You don't have to wait for the question and answer session to begin. We'll try to answer as many questions as possible, but because of the large number of participants today, we might not get to every question. Any unanswered questions will be forwarded along to today's speakers. For basic troubleshooting information, click the Help button located on your screen. At the end of the webcast, you'll be asked to complete a brief evaluation survey. I will let you know more about that after the presentation. This webcast is archived, so you can access it after today's live event. To view this webcast and all of our past webcasts, go to safetyandhealthmagazine.com/events. With that, let's go ahead and get started. Today's webinar includes a panel of 4 seasoned experts. Kathy Abshire is the Welding Safety Solutions Manager at Miller Electric Manufacturing Company. She is an experienced sales professional with a strong background in safety and occupational health. Kathy has worked with numerous leading organizations in manufacturing, industrial distribution, and environmental management. Susan Fiore is the Advanced Applications Manager at Hobart Brothers Welding. Susan has done extensive work in welding safety and health and is past chair of the American Welding Society Safety and Health Committee. She currently serves as chair of the AWS Safety and Health Subcommittee on Fumes and Gases. Also joining us today is Andy Monk, who serves as a product line manager at Miller Electric. Andy works with semi-automatic products within the commercial and construction fabrication markets. His primary focus is on the truck. Our first speaker today is Bert Schiller, who is an industrial hygienist with more than 35 years of industry experience. Bert spent 5 years of his career with Michigan OSHA and has taught at the University of Michigan for the past 5 years. Again, we thank all of you for tuning into this presentation. Bert, whenever you're away.
Thank you. First, a disclaimer. Every welding environment is different and needs to be evaluated by a qualified industrial hygienist or other safety professional to determine the appropriate course of action for fume controls. This presentation is intended for awareness and introductory purposes only and should not be used to replace professional consultation or a complete review of owner's manuals. Let's do an overview of weld fume control. Let's first talk about some basic definitions. Lay people, and especially the news media, often misuse common terms of industrial hygiene. The term fume, for example, is often misused. Technically speaking, a fume is defined as an airborne particulate formed by the evaporation of solid materials. Basically, fumes are only generated from welding, soldering, brazing, or torch cutting operations. The next term is a gas. We all know what gas is. It's one of the 3 basic states of matter, solid, liquid, or gas. Technically, the definition reads, it's a state of matter in which the material has very low density and viscosity. It can expand and contract greatly in response to changes in temperature and pressure. A mist is a suspended liquid droplet generated by the condensation from a gaseous state to the liquid state, or by breaking up a liquid into a dispersed state, such as by splashing, foaming, or atomizing. Think of water mist. Then a vapor. A vapor is a volatile form of a substance that's normally in a solid or liquid state at room temperature and pressure. Though evaporation, liquids can change into a vapor. Again, think of water vapor as opposed to water mist. Let's talk about weld fume factors that can impact an operator's exposure. First is the type of welding process. We're going to talk more about these later in the program. Examples are arc, MIG, or TIG welding. The second factor that can impact an exposure is the base metal or filler metal used. And we're going to talk more about this in the next slide. Thirdly is the location. Is the welding being done outside or is it indoors in an enclosed space? Fourth, welder work practices. Fifth is air movement. Are there cross drafts in the room or is it welding occurring in a dead air space? And lastly, use of ventilation controls, either general ventilation or local exhaust ventilation. I talked about common metals associated with welding. Let's talk about aluminum, mild steel, and stainless steel. These are the three most common base metals that people are welding on. Below that you see iron, nickel, and copper. These are some of the metals that are included in the welding electrode, whether it be a stick electrode or a wire electrode. I could add manganese, which we're going to talk about a little bit more later in the presentation. There's several issues we can talk about in welding. How much welding is being done, for how often, and for how long. Again, what type of welding is being conducted? I already mentioned MIG, TIG, flux core, subarc. All of these generate different levels of fumes and different types of contaminants. What is the base metal? Mild steel or stainless steel? There's a huge difference in fume generation depending on the base metal. I'm going to talk more about hexavalent chromium later in the presentation. Where is the welding being conducted? Is it a well-ventilated area or is it a restricted or confined space? When are there changes that impact your environment? Is it a new or reconfigured workspace? Is there new equipment, new applications? Is it slow production or increased production? All of these are going to affect the level of weld exposure. Now let's talk a little bit about occupational exposure limits. There's lots of different occupational exposure limits. NIOSH sets limits. The American Conference of Industrial Hygienists sets limits. And then there's OSHA. OSHA has permissible exposure limits. OSHA, of course, stands for the Occupational Safety and Health Association and enforces exposure limits for each individual metal, metal oxide, or gas found in the weld plume. Two of the most important of these are hexavalent chromium and manganese. In 2006, OSHA issued its standard for exposure to hexavalent chromium, 29 CFR 1910-1026, if you want to look it up. It established a permissible exposure limit of 5 micrograms per cubic meter and an action level of 2.5 micrograms per cubic meter. And pay attention to those units. Again, these are in micrograms, not milligrams. Most occupational exposure limits are expressed in milligrams per cubic meter. Hexavalent chromium has a very low limit, so it's expressed as 5 micrograms per cubic meter. Manganese. Manganese is present in all welding electrodes, whether it be stick or wire. The current OSHA PEL for manganese was set all the way back in the 1970s, and it is a ceiling limit of 5 milligrams, again, milligrams per cubic meter. A ceiling limit means that at no time should it ever be exceeded. A little while ago I mentioned threshold limit values. These are the limits established by the ACGIH, the American Conference of Governmental Industrial Hygienists. This is a professional society, not a governmental agency. This organization has been around since the 1950s, establishing the threshold limit values. When the OSHA Act was created, they adopted the 1968 TL fees, codified them, and wrote them into law. They adopted the numbers, but changed the names from TLVs to permissible exposure limits. Over the 40 or so years since the original OSHA Act, there's been many updates and changes to the TLV list, so that now the TLV list is quite different than the current PELs, the OSHA limits. For example, again, hexavalent chromium. In 2018, the ACGIH adopted a new TLV for hex chrome set at 0.0002 milligrams, and again, that would be 0.2 micrograms per cubic meter. Manganese, the ACGH TLV changed to 0.02 milligrams per cubic meter as total particulate. So now the manganese limit is 250 times lower than the OSHA PEL. These limits are important when you're doing an assessment of the welding fume exposure. In order to do a proper assessment, you should contact a qualified health and safety professional or an industrial hygienist. It's best to use a certified industrial hygienist, a CIH. This certification is issued by the American Board of Industrial Hygiene, the ABIH. In order to find a qualified hygienist, you might ask your corporate staff. Another source would be insurance brokers or underwriters, or check the AIHA consultants listing for a qualified consultant. Next, we're going to talk about the hierarchy of controls, which is Industrial Hygiene 101. On the next slide, you see the hierarchy of controls. The first and best solution for any problem is the elimination or substitution of a less hazardous material for a more hazardous material. The next best solution are engineering controls, whether it be local exhaust ventilation, general ventilation, or some other type of engineering control. Followed by work practices and administrative controls. And then finally, the last line of defense is personal protective equipment. That's it for me for now. I'll come back on later, but I'm going to turn it over to the next speaker at this point.
Thank you, Bert. This is Susan Fiore, and I'm going to be talking today about process modification and substitution. Process modification and substitution is the first step in the hierarchy of controls. It is also the most effective since it removes or reduces the danger to the environment, thereby protecting not only the welder, but also those workers in the surrounding area. The first option for process modification is to eliminate welding, but since this is a welding safety presentation, I'm not going to get into that. Other options include modifying the process, which can include changes to the process itself, as well as changes to the welding parameters. Automation is another process modification that can help to reduce exposure to welding fumes. Changes to the materials, including the filler metal, the shielding gas, and the base material, are another way to reduce welding fume exposures. Keep in mind that these sorts of changes may require you to recertify your welding procedures. This slide shows how changing the welding process, and in some cases the shielding gas, can help to reduce the amount of fume that is generated. Processes like gas tungsten arc welding and submerged arc welding tend to be very low in fumes. Unfortunately, GTAW is also very low deposition and requires a high degree of welder skill. Submerged arc welding, on the other hand, can only be used in the flat and horizontal position and may require a large investment in equipment. Solid wire gas metal arc welding tends to be relatively low fuming, especially if pulse transfer is used with high argon mixtures. I'll talk a little more about that later on. There are a variety of flux and metal cord welding products, some of which are designed specifically to be low fuming, and others that may target specific elements, such as manganese or hexavalent chromium, in the fume. This slide shows the effect of shielding gas on fume generation rate for gas metal arc welding. The results are similar for flux cord arc welding. The bottom line is that the less active the shielding gas is, that is, the higher the argon content, the lower the fume will be. Another option is to choose a filler metal that targets specific components of the fume. This graphic gives a comparison of manganese exposure using a low manganese flux cord wire as compared with a traditional flux cord wire. Reductions in manganese exposures of 50% or more are possible with these low manganese filler wires. You should note that this testing was done in our test lab under controlled conditions. You should always do exposure testing in your own facility to verify the results due to the large number of variables that affect fume exposures. I think Bert mentioned some of these variables, but they include things like the specific welders and how they position themselves relative to the fume plume, the welding parameters, the room dimensions, local exhaust ventilation, the number of welding operations, etc. As I mentioned earlier, the type of weld metal transfer can have a significant impact on the fume generation. Modified short-circuiting transfer provides a more stable arc than conventional short-circuiting transfer, which can help to reduce fumes. It's also been found that switching from conventional spray transfer to pulse transfer in gas metal arc welding can significantly reduce welding fume. Keep in mind, though, that a simple change to pulse may not result in the expected decrease in fume generation. You may need to optimize the welding parameters to get the desired results. You should contact your welding supplier if you need assistance. Also note that we do not see a similar reduction in fume when we use flux and metal cord wires with the pulse transfer. In summary, there are many advantages to lowering welding fume generation by modifying or changing the welding process, the greatest being that it helps to protect the welder as well as the people working in the surrounding area. It can also be a way to target specific fume constituents, such as manganese. And finally, these types of changes are generally relatively simple to implement. Some of the disadvantages of modifying the process include the possible need to invest in new equipment, as well as the need for additional training or requalification. You should also keep in mind that not all processes will work in all situations. Things to consider include the deposition rate, positional capabilities, and mechanical property requirements. Finally, if you are considering switching shielding gas, keep in mind that argon gas mixtures are typically more expensive than CO2. The second tier on the hierarchy of controls is engineering controls. Engineering controls are the second most effective level of control. Implementation means controlling the hazard through a physical change to the workplace or a change in the design of equipment, such as improved ventilation. Types of engineering controls include local exhaust ventilation, process enclosure, and general ventilation and filtration. Local exhaust ventilation, also called source capture, means the contaminants are removed at their source before they reach the welder's breathing zone. Examples include extraction arms, backdraft hoods, downdraft tables, and fume extraction guns. Process enclosure means creating a barrier, such as an automation hood, between the operator and the process. Finally, general ventilation and filtration would include things like HVAC systems that move large quantities of air to dilute or filter out contaminants. With that, I'm going to turn the presentation over to Andy Monk, who's going to tell us more about fume extraction guns. Andy?
Thanks, Susan. A little bit more about fume extraction MIG guns, and specifically, how do they work? Well, fume capture, they capture fumes generated by the welding process right at the source, over and around the weld pool. They can be tailored to best meet needs of a specific application or to welder preferences. And they're ideal when the welder is in a tight or confined space or must move often to complete welds on a large part. A little bit about best practices when using a fume extraction MIG gun. It's always good practice to pause at the end of each weld to accumulate any residual fume. Frequently inspect the front of the gun for damage or spatter buildup that could inhibit fume extraction, and routinely inspect the vacuum hose for cuts or tears, as this will negatively impact the gun's ability to extract fume. Fume extraction guns are available in a variety of amperages and handle designs. Common amperages for fume extraction guns range from 300 to 600 amps. Keep in mind that amperage is tied to gun weight. The higher the amperage, the more copper required in the power cable, and therefore the heavier the gun will be. Due to this additional weight, use the lowest amperage gun possible that will still allow the job to be completed. Along with the added weight, higher amperage guns typically cost more than lower amperage guns, so it may be a waste of money to buy more gun than necessary for the application. However, automatically buying the lightest gun available may not provide the amperage or durability needed for the application. Some lighter and more flexible guns aren't durable enough for heavy industrial applications. Always consider a gun's duty cycle rating, and keep in mind that it's a balancing act between gun weight and durability when choosing a fume extraction gun. Some features to consider. An adjustable vacuum chamber provides better joint access and visibility and helps welders dial in vacuum flow to eliminate porosity. A suction control valve can work in conjunction with an adjustable vacuum chamber to balance suction with shielding gas flow to protect against porosity. A flexible and crush-resistant vacuum hose eliminates the need for a protective hose cover in many applications while reducing overall gun weight and increasing flexibility. Tailoring the gun handle and neck to the application and welder preference can help improve weld access and reduce operator fatigue. A common consumable platform means many consumables used on a standard MIG gun or even a robotic MIG gun can also be used on a fume extraction MIG gun. When fume gun replacement parts, such as nozzles, contact tips, and gas diffusers, can be the same as those used on standard MIG guns, this offers greater flexibility and helps reduce the company's consumable inventory. Now I'll turn it over to Kathy for information on fume extractors.
Thanks, Andy. So I'm going to be talking here about some of the different solutions that are available for different uses. Fume guns are a primary source capture device. However, they might not be a viable option for all the weld processes or for your specific application. So you may want to be able to consider different applications for your work environment. So for processes such as welding, brazing, and cutting, another form of engineering control is fume extractors, also known as a type of local exhaust ventilation, which can be effectively capturing the welding fume before it reaches the operator's breathing zone. So let's just take a little bit deeper look at several types of fume extraction systems that are available to consider. There are portable units that are used in areas where the weld environment and location constantly changes, such as maintenance and repair or light-duty welding, where portability is a key to the condition of work. Mobile systems are great for medium and heavy welding operations that are in open work environments, such as open bay or floor areas where mobility is the key to be able to do the work. There are stationary systems that are also used in medium and heavy welding that takes place in larger weld cells or an area that is always consistent, where floor space might be limited and where wall-mounted or pedestal mounting is required. Centralized solutions for source capture are optimal for heavy and larger weld areas. This is normally where the area might have multiple cell booths and multiple extraction arms that are used with only one collector for a filtration device. A second method related to fume extraction is considered general ventilation. Now, this method is typically seen in HVAC systems which use ambient air cleaning. These systems are very effective in moving large quantities of air that dilute the contaminants or filter them based upon air exchanges within the facility. And that's great for the entire shop environment. However, these systems do not collect weld fumes at the source, and therefore it would be necessary to evaluate other means of protecting the welding operator, such as respiratory protection. A third method, and actually OSHA's preferred method of engineering controls, is process enclosure. This is an ideal solution for fume extraction as it physically creates a barrier between the operator and the weld process, removing the operator from the hazard. Enclosures such as curtains and other structures seen here with an automated hood that actually isolate the weld fume from migrating into other areas of the plant where other employees are working. However, this method does require a source of filtration and collection for the welding fume. Most commonly, this method is used with a fume extraction hood covering the entire area of the weld cell, which is then connected to a filtering mechanism such as a stationary or a centralized filtering system, which is able to capture the welding fume over the weld area. However, when selecting the appropriate fume collector for your environment and your process, there are a few things that you need to be aware of that may impact the performance of the device itself. Depending upon where the welding is taking place or the size of the weldment and the access to the joints, those factors may impact the performance of the extractor, such as the work environment that has open bay areas with those large doors or mechanical fans that can cause the weld plume to travel to other areas of the plant, impeding collection by the extractor. The size of the weldment and the number of joints to be welded may also require proper placement of the extraction device and needs to be positioned with proper distance to the capture zone, and that needs to be positioned as well to pull the fume away from the operator and not past their breathing zone. With larger weldments, you may need to consider the mobility of the welder and the multiple movements that might be required to position the device properly to capture the welding fume. There are other equipment also in the shop environment, such as overhead cranes, ducting, and other structures in the manufacturing process that might also interfere with the type of collector that's selected or the placement of the device that might limit access to the weld and the collection of the welding fume. Another consideration in selecting your fume extraction device is the type and amount of welding that you're doing and how that would impact the performance and the efficiency of the filter element in the collector itself. Factors do affect the life of the filter and the replacement and consumable costs of the filter as well. In general, there are two types of filters, disposable or self-cleaning, that are primarily used in fume extraction systems. Disposable filters are best suited for light-duty application with lower arc-on time, such as the maintenance and repair operations, or for specialized jobs that would require frequent use and replacement of filters. These filters are normally at a lower cost of an investment initially, but they also have a lower filter life. Self-cleaning filters then are best suited for heavy to medium weld applications where the fume extractor actually has a mechanism to remove the weld particulate off the filter. That then deposits into a collection basin and actually maintains a consistent airflow during the use of the filtering system. This method also increases the efficiency of the filter and increases the filter life up to about 8 times longer than the disposable filter, reducing labor costs and cleaning. Although self-cleaning filters are higher in cost initially than disposable filters, usually you can receive a return on investment that can be recognized after approximately 6 cleanings of the filter. Now, there are also things that will impact the filter efficiency and the life of the filter. The amount and type of welding that's being done, and the fume generation rate, types of welding processes that are being used, and the actual arc-on time are certainly going to affect the life of the filter. The quantity and the type of the weld with fumes, such as whether it be welding or cutting or brazing, and the number of hours in operation are also going to affect the performance and life of the filter. And depending upon the cleanliness of the parts being welded, or the amount of oils and anti-spatter, rust inhibitors that will also collect on the filter, may also decrease the filter efficiencies. There's an amount of moisture and humidity of the weld environment that could also affect the filter. Now, all of these factors play the role in the efficiency and life of the filter and should be considered in your decision in selecting the appropriate fume extractor for your specific application. Now, in reviewing the engineering controls for fume extractors, These methods have advantages and disadvantages in the use and performance. It's important to remember, as Susan had mentioned, is that not all solutions are going to be feasible in all environments, and that there are many considerations in evaluating source capture for your workplace. But some of the key advantages are that these engineering controls actually capture the weld fume before reaching the breathing zone of the operator. And as a result, the workplace environment is improved and regulatory compliance is increased. And there are several solutions for source capture and fume extraction, as we reviewed, for almost every welding application that is out there. Although there are some limitations and disadvantages that we need to be aware of. Some plants have footprints that have space constraints and may require physical changes to the weld environment to be able to accommodate for implementing engineering controls, such as implementing general ventilation, centralized systems, or moving fume extractors around the plant. Also consider the labor and the consumable costs for maintaining these mechanical systems, implementing routine maintenance schedules for filter replacements, and proper disposal of the welding fume. There's also the possibility of the loss of production due to the result of the amount of time required for the operator to interface with a source capture arm, which can be a disadvantage in performance. I'm going to now walk us into the third tier of the OSHA hierarchy of controls, which is work practices, or also known as administrative controls. Now, these controls limit the worker's exposure by scheduling reduced work times in contaminated areas or by implementing other work practices or policies. Generally, administrative controls can be difficult to implement and maintain, and they're not always reliable, as these have limitations and the hazard is not removed. It's always best when administrative controls are used in addition to engineering controls. So in relation to the weld environment, let's take a look at a few of the high-level activities or changes to workplace procedures and the way people work in the weld environment that can limit or prevent exposure to welding fumes. Training on proper body position to keep the welder's head out of the plume will limit exposures to welding fumes at the breathing zone. Also, training on proper positioning of weld equipment such as mechanical fans, the fume extraction arms, to work effectively will also reduce limits to exposures. Increased visibility and optical clarity on welding lenses will allow the welder to see more clearly and encourage better body positioning. And actually, proper training on the weld process and the proper use of the welding equipment can reduce weld spatter, fume generation rates, reduce overwelding, and the need for cleanup and rework. Although administrative controls may seem to be more difficult to implement, the key consideration is training. It is an essential element to augment all work practices to successfully implement changes needed to limit exposures to welding fume through behavioral change. Of course, when we're making changes to the workplace policies, there are impacts that also should be considered. A few of those advantages, as we mentioned, is that increased productivity and reduced labor costs can be the result of training on proper weld technique, reducing scrap and the need for rework. Enhancing visibility for the operator can lead to higher productivity rates and lowering the risk of exposure to harmful rays or debris in the eye. And training on best practices in the weld process can also result in increased safety and increased compliance ratings. The largest disadvantage in implementing an administrative control or changes to the workplace policies is that implementing a training program and introducing equipment may require significant investment in allocating dedicated resources and time to effectively manage and maintain these programs over time as the changes occur. Some administrative controls will also require physical changes in the weld environment and operator behavior. So collaboration and welder acceptance will be key in order to successfully implement these changes, which some environments may be difficult to achieve. We're also going to talk about the fourth tier in the OSHA hierarchy of controls, personal protective equipment, and as it relates to the welding environment, we'll talk about respirators. It's important to note that OSHA states that PPE, or respirators in this case, should only be required when all other methods of controls have been explored. The respirators do create or impose a barrier between the worker and the hazard, preventing them from inhaling hazardous substances or contaminants. It's very effective in protecting the operators from inhaling contaminants in the weld environment, such as dust and fumes and vapors and gases. However, not all respirators are effective in protecting against all contaminants, and careful selection needs to be considered for each application in the weld environment. OSHA states that there are specific recommendations when respirators should be implemented as a method for protection, such as if engineering controls are not feasible, or if the levels of exposure are not reduced to OSHA PELs or below through other control methods, such as the engineering or administrative controls. Respirators can be used in maintenance or emergency situations and during the installation of other fume management solutions, such as local exhaust ventilation or centralized extraction systems. Now, when respirators are implemented as a means of personal protective equipment, there are very specific responsibilities for employers to identify, select, establish, and implement a formal respiratory protection plan. That can be found in the OSHA 29 CFR 1910.134. What OSHA states is that a respirator shall be provided to each employee when such equipment is necessary to protect the health of such employee. The employer shall provide the respirators which are applicable and suitable for the purpose that it was intended. And the employer shall be responsible for the establishment and maintenance of a respiratory protection program, and that program shall cover each employee required to wear and use a respirator. So this respirator program, pretty in-depth, must also address how to find out what hazards are present in your environment, how much protection the worker is going to need, and describe how to wear and maintain and store the respirator after use. The program should be administered by a suitable trained program administrator. It's a pretty in-depth program, and we're going to cover some of the critical steps here for compliance. But in 2019, one of OSHA's top 10 violations, ranking in at number 5, is the Respiratory Protection Program, totaling 2,400 violations. Some of the most cited issues were failing to establish a program, failing to perform required fit testing, and failing to provide medical evaluations were most of the cited issues. So let's take a look at some of the critical requirements for complying with the written respiratory protection program. Now, there are two uses of respirators within a facility, the first being a mandatory use and the second being voluntary. So when a mandatory use of respiratory protection is required, the program must include these critical factors: respiratory selection, the use and maintenance and operation of that protective equipment. Medical evaluations are to be performed to examine the medical and physiological fitness of the workers before they're assigned to work in the areas where the respirators are required. This is normally performed through a questionnaire that can be found in the standard itself, and then possibly followed up with a physical examination to be certain that the worker is physically fit to carry out the work task while wearing the respiratory equipment. Fit testing is required for all fitting respirators under the mandatory requirement, and workers need to be clean-shaven while wearing the respirators. So this is an ongoing process, and the program should be updated as necessary to reflect any changes in the workplace conditions that might affect the respirator use. So it's really important and key to always do air sampling to ensure air quality is maintained below OSHA PELs following any process changes within the weld environment. And those process changes could include change in the process, change in the base metal or materials, and change in any of your engineering or control methods that have been used. Employee training is also very key and is required for all types of respirators that are mandated to be worn within that environment. Voluntary use. Not all environments require the use of respirators, and using a respirator can be an effective method of protecting against designated hazards when properly selected and worn. And some employers will encourage the use of respirators even when exposures are below the PEL. And that's to provide additional level of comfort and protection for the workers. And sometimes you might find that your own employees will be wearing respirators to avoid exposures to hazards, even though the amount of the substance in your environment does not exceed OSHA's limits. So if you're going to be providing respirators for voluntary use or employees provide their own respirators, there is certain precautions that need to be addressed through a written respiratory protection program. However, it's not as extensive as the mandatory use. You can find the requirements for the voluntary plan on the Appendix D of the 1910.134 respiratory standards. Note that that does not apply to wearing dust masks in the work environment. Now, there are some respiratory terms that are really important in the selecting of an appropriate respirator for your work environment. Different types of respirators offer different levels of protection, and these three major terms actually interrelate with one another to be able to guide you to select the appropriate respirator for use and protection in your weld environment. And the first term is the assigned protection factor, which is the measure of the respirator's protection capability. So this actually applies to the respirator itself and to the level of protection or class of respirators that is expected to provide the employee when the employer implements a continuing, effective, and respiratory protection program. Now, this is a number that is assigned by OSHA to the respirator for the level of protection from the airborne exposures. So the larger the number, the greater the protection. For example, when properly used, a respirator with an APF of 10 will reduce your exposure levels to 1/10 the concentration of the contaminant in the air. Similarly, a respirator with APF 50 will reduce the exposure to 1/50th of the concentration of the contaminant in the air. So the second relative term is the permissible exposure level, and Bert had referenced that earlier, and that is the acceptable amount or concentration of substance in the air in the work environment. Now, OSHA has established PELs that are intended to protect the worker from any adverse health effects related to the health exposures. And a third term used in selecting respirators is maximum use concentration. This refers to the maximum amount of atmospheric concentration of any hazardous substance from which the employee can be expected to be protected when wearing a specific respirator. So these are all interrelated, and the maximum use concentrations can be determined by multiplying the APF of the specified respirator by the OSHA's PEL to get your maximum use concentration. So as an example, with manganese, the permissible exposure level for manganese is 5 milligrams per cubic meter. If we're using a half-mask respirator, which has an assigned protection factor of 10, the maximum use concentration, or the maximum exposure, wearing that half-mask respirator would be 50. So it's really important to know where your contaminant levels are within your facility by doing air sampling. And knowing the APF of the respirator and the PEL of the contaminant, you'll achieve your maximum use concentration and help make a better decision on the proper selection of respiratory protection for your specific environment. So let's take a look at a few of the respirator types that are found in the welding environment. And there are two. The first is the air purifying respirator, and the second is the atmosphere supplying respirators, which we'll discuss shortly. So air purifying respirators are shown here. They contain filters or cartridges that actually remove the contaminant in the air by filtering out the particulates such as a dust, metal fume, or a mist, and creating a barrier to the breathing zone when properly worn. The most common type of respirators used for protection against welding fume and solid particulates are disposable particulate masks such as dust masks, which have an APF of 10. Reusable half masks with replaceable filters, many which are tight-fitting, and fit testing is required, and these provide an APF also of 10. There are powered air purifying respirators which have a loose-fitting hood or a helmet with an auto-darkening filter lens and a belt-mounted blower that filters the air from the weld fume and delivers fresh air into the hood. Now, these are not tight-fitting, they do not require fit testing, and they provide higher protection factors of 25 or 1,000. Now, the second type of respirator we talked about was atmosphere-supplying respirators. Now, these systems provide filtered grade D breathable air from an uncontaminated source. One of the most common systems found in the welding environment is the supplied air respirator, or SAR, and that delivers filtered air from an external source, such as an air compressor, through a purification panel board or box, and a supplied air hose to the welder's helmet. Now, additional configurations may include a Type D cylinder of breathable air as the air source, or a tight-fitting mask as well. Many of these systems provide the benefit of having continuous airflow delivered into the hood, can be air-conditioned, providing relief in hot environments, and providing maximum protection in confined spaces. These systems can provide anywhere from an APF of 25, 50, or 1,000 as well. Now, within the respiratory protection offerings, there are two classifications of respirators. We talked about this just briefly. There are two types, tight-fitting respirators and loose-fitting respirators. And each of them have certain features and requirements under the OSHA respiratory protection standard. Tight-fitting respirators such as the half mask or a full-face respirator has a respiratory inlet covering that forms the complete seal between the respirator's facepiece and the user's face. So fit testing is always required for mandatory use of these respirators, also to be clean-shaven, to ensure that they fit properly and can provide the APF that's expected of the level that is assigned. There are two methods of fit testing that have specific protocol under the OSHA standard as well. There's qualitative and quantitative fit testing. Qualitative fit testing is a pass or fail test method that uses the sense of taste or smell or our user's reaction to an irritant in order to detect leakage into the facepiece. And quantitative fit testing uses a machine to measure the actual amount of leakage into the facepiece itself. Qualitative fit testing can be used for any type of tight-fitting respirators. There's usually a probe that is attached to the facepiece that would be connected to the machine to be able to calculate the quantity of air that is leaking. Again, as I mentioned, there are specific protocols under the OSHA respiratory standard for each of these fit testing methods that must be followed. Loose-fitting respirators such as helmets or hoods do not depend on a tight seal with the face to provide the protection. They have a respiratory inlet covering that forms a partial seal with the face and therefore does not need to be fit tested, even when mandatory use is necessary. So facial hair is acceptable under the seal of this helmet assembly. Now, it seems that choosing a respirator can be a complicated matter, but with the guidance of an experienced safety professional or occupational hygienist or someone who is very familiar with your actual workplace environment, the selection of the proper respirator for your welding environment can actually provide many benefits. The decision includes considering the limitations and the types of the respirators that we actually just talked about. But some advantages are that respirators, when appropriately selected and worn properly, create the barrier from contaminants entering into the user's breathing zone. And some respirators, such as PAPRs and supplied air systems, provide coolness in hot environments, producing a source of heat stress, relief, and productivity. These also aid in reducing fogging of safety glasses and welding lenses in humid environments. And using respirators with hoods and helmets can also increase safety for the eye and face protection and meet compliance requirements with more stringent TELs or TLVs that are ever changing. While the largest disadvantage in the consideration of implementing respirators as a means of protection is the effort needed to comply with the OSHA standard for respiratory protection. As a last means of protection according to the OSHA hierarchy of controls, engineering and administrative controls should always be explored first. Implementing a written respiratory protection plan is a significant investment of time and resources to develop, manage it, and change as it is an ongoing process. Consider the initial investment of the program and the medical evaluations, the initial purchase of the equipment and replacement and consumable costs for respirators, and the maintenance required for sustaining that program. Be aware that wearing a respirator device may place burden on some employees. There may be physical as well as psychological conditions to be considered, such as medical fitness and feelings of claustrophobia that might be present in some employees. So today we've covered a multitude of feasible and effective control methods of the OSHA hierarchy of controls as it relates to the welding environment. And hopefully we've provided you with some insight and guidance on evaluating solutions that might be right for your welding environment. A few key thoughts, though, before we close and before I turn it back over to Bert, is to keep in mind that this is a tiered approach toward a dynamic result. There are multiple solutions that may be necessary to reach your compliance goals, and evaluation of these control methods is an ongoing process and may require testing and retesting, especially as the workplace and regulations continue to change. Success for implementation is a collaborative effort among a team of manufacturing, engineering, production, and safety resources would create the best desired results for your weld environment. So, which solution is right for you depends on the dynamics of your weld environment. Now I'm going to turn this back over to Bert so he can summarize up our session for today.
Thank you. Again, a quick review of overall process. It's not as complicated as people think. Remember the hierarchy of controls, starting with substitution of a safer way of doing it, followed by engineering controls, work practices, and PPE. It's very important to control the air quality in the plant, not only for the comfort and of the people doing the welding, but compliance with regulatory obligations. The benefits of controlling your air quality include reducing indirect costs, such as lowering insurance premiums, protecting you from OSHA inspections and fines, and it helps to improve the recruitment and retention of skilled workers. So thank you very much for attending. I'm going to turn it back to the moderator to introduce some questions that we'll try and answer for you.
Excellent. Great job, Bert, and great job to everyone. We thank you all for your insights and expertise. Before we do start the Q&A, I do want to remind everyone of the evaluation survey that we're asking you to complete. The survey should be appearing on your screen now. Your input is important because it'll help us improve future webcasts. If you don't happen to see the survey on your screen, please turn off your pop-up blocker. You may also access the survey by clicking the survey button near the lower right part of your screen. And with that, we will get to some questions. Bert, this first one is addressed for you, and it is, what was that about, it's, will OSHA adopt as its PEL the lower ACGIH TLV for manganese?
From what I'm reading and hearing, not anytime soon. As you know, the regulatory environment in Washington right now goes at a pretty slow pace, so I don't anticipate the manganese TLV being adopted anytime soon.
All right, thank you. Kathy, this one is addressed to you. How effective are the fume extractors? What documentation do you have that verifies using filters is effective in controlling exposures versus exhausting fumes outdoors?
Well, one of the key things is also to ensure the collection of the welding fume is the proper positioning and placement of the fume extractor itself, and then also the filter media that is in the extractor, and making sure that it is able to collect the particulate size for the welding fume. So there are many different filter medias in the marketplace. There are many different types of fume extractors and ability to suck the fumes away. So it's really important to look at the specifications of each device that you might be considering.
All right, Bert, another for you, and it relates to welding on galvanized items outdoors. What are OSHA's approved methods for controlling fumes in terms of mechanical and also natural ventilation means?
Well, of course, welding on galvanized introduces the risk of being exposed to zinc oxides. Zinc is present in galvanized metal. I can't give you a hard and fast answer. Obviously, it depends on the conditions outside. If you're outdoors and there's a breeze, and if you're properly positioned with good work practices, the wind is at your back, you may not need any local exhaust ventilation. If you're in an enclosed or area where where there's sides or a cover over the area where you're working, you still might need to have some local exhaust ventilation. So it depends on the conditions. Common sense prevails in this case. And then lastly, if respiratory protection is required, even in an outdoor environment, then you should wear it.
Got another for Kathy. Could you please talk a little bit more about TIG welding fumes and the type of extractors needed?
Well, regardless of the weld process itself, it really depends on the amount of concentration for that environment or the exposure level to the employee. So whether it's TIG or MIG or an electrode, it really depends upon the amount of exposure to that fume. In regards to weld extractors, you can use extraction devices for any of those processes. The importance there, as we talked about, is what type of welding you're doing, where you're doing the welding, the process that you're using, and then the filter media can be affected by cleanliness of the part or how often that you're actually utilizing that fume extractor and the performance of that filter. So whether it be TIG or MIG, it really also comes down to the exposure level of that process and the type of process that you're doing, but fume extractors can be utilized, of course, for all of those welding processes.
We've got another Bert question. Is it possible to measure in real time during welding operations the concentrations of contaminants such as manganese or hexchromium that the operator is exposed to?
Not under current technology. You can't analyze individual metals in real time. What you can do in real time is measure the total amount of fume. There are direct reading devices that work on photometric principles, so you can get real-time data expressed in milligrams per cubic meter for total fume content. And if you know from prior data what percentage might be manganese or iron or chromium, etc., that does give you some indication. So no, not specifically for the individual metals, but yes for total weld fume.
Okay, we've got time for one more question, and it goes to Andy. Says that California requires either local exhaust ventilation of SAR for MIG welding stainless steel. Would a fume extraction gun be a viable option here?
Yeah, it definitely could be. Everything is really application dependent. So if you've got an application where it's tough to control fume in other ways, and this type of engineering control is a good fit because maybe it's a big piece of equipment that doesn't allow other methods to control fume, then yeah, it could be a viable option. But every situation is a little bit different, and it would be great to pull in an industry expert to take a look at the application just to verify for sure.
Okay, well, again, we thank you, everyone. Unfortunately, that we've run out of time today. Sorry that we didn't get to everyone's questions, but all of today's unanswered questions will be forwarded on to our speakers. Once again, we hope you take the time to fill out the evaluation survey on your screen to give us your feedback. With that, we end today's Safety and Health Magazine webcast. I'd like to thank our speakers, Kathy Abshire, Susan Fiore, Andy Monk, and Bert Schiller, along with everyone at Miller Electric Manufacturing Company and all of you who listened in. Thanks, and have a great day.